Hello everyone, myself Munab Bhangi. I am studying in BSc 4th semester. My assignment topic was carboxylic acids and their derivatives. Let's study the acidity of carboxylic acid. Carboxylic acids are acidic because they can release a proton to form a carboxylate ion. The acidity of carboxylic acid mainly due to the resonance stabilization. Here the resonance stands for electron movement between structures. The acidity is primarily due to the resonance stabilization of the carboxylate ion. The negative charge is delocalized over two electronegative oxygen atoms, making the ion very stable. As we know, the negative charge is not fixed on one oxygen. It is shared between the two oxygen atoms. Also, both oxygen atoms are highly electronegative and they can hold negative charge effectively to make the ion very stable. For understanding, for example, imagine two people sharing weight instead of one person carrying it alone. It became easier and more stable. Similarly, the negative charge is shared between two oxygens, making the ion stable. Next we study effect of substituents on acidity of aliphatic and aromatic acids. The acidity of a carboxylic acid is greatly influenced by the nature of the group attached to the carboxylic group. In aliphatic acids, here there are two type of groups, electron withdrawing groups and electron donating group. In electron withdrawing groups like chloro, nitro or cyano increases acidity. Through the inductive effect, they pull electron density away. And also the negative charge on the carboxylate ion become more stable. And also just think of electron withdrawing groups like a magnet pulling electrons away. This reduces the burden of negative charge on the ion and making it more stable and increasing acidity. An example for this, chloroacetic acid is stronger and the acetic acid is weaker. In electron donating groups like alkyl groups decrease acidity. They push electron density towards the carboxylic group, destabilizing the carboxylate ion. In aromatic acids, we see in the electron withdrawing group at para-meta increases acidity. Example, para-nitrobenzoic acid is stronger than benzoic acid. Para-nitrobenzoic acid is significantly stronger acid than the plain benzoic acid because that nitro group is working hard to pull those electrons away. In electron donating group at para-meta decreases acidity. Methoxybenzoic acid is weaker than benzoic acid. It is weaker because the methoxy group is crowding the area with extra electron density. The ortho effect. All the substituents in the ortho position increase the acidity of benzoic acid regardless of whether they are electron withdrawing or electron donating. This is largely due to the combination of steric and electronic factors that disturb the planarity of the carboxyl group with the ring. However, the position matter more than personality of the group. Almost any group placed in the ortho position will increase acidity, whether it's an electron puller or electron giver. However, almost any group attached to the ortho position of benzoic acid will increase its acidity. These effects occur regardless of whether the substituent is electron withdrawing or electron donating. The bulky ortho substituent creates steric crowding. This forces the carboxylic group to twist out of the plane of the benzene ring. And also, on by breaking the planarity, resonance between the ring and the carboxylic group is disrupted. However, this stabilizes the resulting carboxylate ion, making it easier for the molecule to release a proton and also thereby increasing acidity. Last we study Hell Walide Jelinski, nothing but HVZ reaction. This reaction is used to substitute a halogen at the alpha carbon of a carboxylic acid. Normally, carboxylic acids are quite stubborn, unlike aldehyde or ketones, and they don't like to react at the alpha carbon. We want to replace an alpha hydrogen with a halogen, and we use red phosphorus to activate the acid to make it reactive. Before starting the reaction, check your molecule. Requirement: the carboxylic acid must have at least one alpha hydrogen. General reaction, and last there is a product, an alpha halocarboxylic acid. These products are useful intermediate for synthesizing alpha amino acids or alpha hydroxy acid.